Hello everyone, Mehdi Mortazavi here with an example from the properties of real gas. In this problem, we are going to study water vapor at two different states. This is state 1, pressure of 1000 kPa and temperature of 600 degrees C. And in state 2, the pressure is reduced to 500 kPa and temperature of 400 degrees C. So this is state 2 and pressure and temperature. The question is asking for the change in enthalpy or H for this water vapor. And in part A, we are just going to use the superheated vapor tables. So pretty simple in part A. So let's say before that, let me just write down the two states that we have. We have state 1, and in this state, water vapor has pressure of 1000 kPa and temperature of 600 degrees C. And also we have state 2, pressure is dropped to 500 kPa and temperature is equal to 400 degrees C. Okay, so at this time we should be able to obtain the phase of water by having the pressure and temperature. So we can easily tell that the phase is superheated vapor by going to the table and, for example, reading at the saturation temperature at this particular pressure, and you will see that saturation pressure for this pressure is less than this. So that means we are in superheated vapor region. So I go to the corresponding table. I go to table A6 for superheated vapor table, and I will read H1 equal to 3698.6 kilojoule per kilogram. So this enthalpy is coming from table A6, which is for superheated vapor, and that is for water. I use the same table A6, and by the way, when I say A6, I am referring to the table that we have in this textbook. I'm referring to this textbook basically, and these are the authors. So in table A6 of that particular textbook, H2 is obtained at 3272.4 kilojoule per kilogram. So based on that, I can obtain H2 minus H1 that the problem is asking for. And H2 is 3200, H1 is 3600, almost 3700. So H2 is less than H1, and the difference between them is negative 426 kilojoule per kilogram. And this is basically the answer to part A. Okay, now in part B, the question is asking to find that difference in enthalpy, but by using the departure chart. So what I need to do in part B, I want to go back into the correlation that we had before, which was basically, let me show you the correlation. Basically, we want to utilize this correlation. This is what we want to use. H2 bar minus H1 bar is equal to H2 bar minus H1 bar ideal minus RU, which is the universal gas constant, the critical temperature, the difference between ZHs. And ZH are the enthalpy departure factor, which is coming from figure 829. So I want to use that correlation this time. So in another video, we also use this correlation, but in that video we only had one phase. In this problem we have two phases, so I'm sorry, two states. So basically I want to use state 1 and state 2. In the previous video we only had one state, not just one phase. We had one state, and I was just using one of the subscript. Now let me write down the correlation once again. So the correlation says H bar 2 minus H bar 1 is equal to H bar 2 minus H bar 1 with subscript ideal minus RU T critical ZH2 minus ZH1. Okay, so I need to find a couple of things. One of the things that I need to find is H bar ideal. So basically, H bar ideal means if the steam or the gas is behaving ideally. Okay, so I can obtain them from table A23. For, let me just write it down here. For state 1, which is this state here, H1 H bar 1 for ideal is equal to 3754 kilojoule per kilomole. Okay, so this is basically coming from table A23. You know what, because I don't have that much space, I'm just continuing that here. So let's say for state 1, H bar 1 is equal to 30754 kilojoule per kilomole, and this is coming from table A23. And by the way, this is H bar 1 ideal, if we assume the steam is behaving ideally. So I added this ideal subscript. I will do the same thing, H bar 2 ideal, assuming that steam is behaving ideally. And what I would do, I'm going to use the temperature, go to the same table A23 and obtain H bar, and that will be 23,081. So this is also coming from table A23. Okay, so basically I'm good with these two H bars. Basically this is checked, this is checked. Ru is also known, this is 8.314 kilojoule per kilomole Kelvin, which comes from table A1. Okay, table A1, you do not need to memorize that value, you can easily go to the table, just go below the table and the very first line gives the value of 8.314 kilojoule per kilomole Kelvin. Cr is the critical temperature, and I would need that. So before putting the numbers into these, I need to find ZH values. Okay, I need to find ZH1 and I need to find ZH2. So ZHs are coming from A29. Okay, so the name of ZH once again is enthalpy departure factor, which is coming from A29, figure A29. If you go to that figure, we have PR on the horizontal axis, and we have reduced temperatures, let's say in this particular case, in different curves, and the vertical axis or the y-axis is ZH. So this is what you have in that table or figure. Okay, so for point 1 or state 1, basically, TR or the reduced temperature is equal to temperature over the critical temperature. The temperature is given at 600 degrees C, but you really want to be careful because for correlations like these that we are looking at the ratio of the temperature, the unit of temperature should be in Kelvin. So I'm converting from 600 degrees C to Kelvin, and that will be 873 Kelvin. The critical temperature of water is 647.1 Kelvin, which again comes from table A1. So the critical properties are coming from table A1. So in that table, you want to go and find the reduced temperature and reduced pressure for water. Okay, so that gives you TR value equal to 1.34. Likewise, the reduced pressure is equal to the pressure divided by the critical pressure. Okay, the pressure at state 1 is 1000 kPa, so that is 1 megapascal, and the reduced pressure, the critical pressure is 22.06 megapascal, and that will give you a reduced pressure of 0.0453. 3 for state 1. So if you use these two numbers and go to A29, figure A29, I mean, that will give you ZH, but because that is for state 1, I add subscript 1 equal to 0.0288. So in this correlation, in this equation, ZH1 is checked, but I can use the same concept to find ZH2. So let's say for state 2, I have reduced temperature, which is T over T critical. State 2, my temperature is 400 degrees C, so that will be 673 Kelvin over the critical temperature, which is 647.1 Kelvin. And that will give me the reduced temperature of 1.04, which is a unitless or dimensionless number because that's Kelvin divided by Kelvin. Likewise, my PR is pressure over the critical pressure, and pressure is 0.5 megapascal, converting from kPa to MPa. Be careful with the units because the unit of critical pressure is in megapascal, 22.06 megapascal. And that will give me 0.0226 for the reduced pressure. So again, you will use these two values, go to A29, and that will give you ZH2, enthalpy departure for state 2, and that is 0.0223. Okay, so you will see that these two ZH values are in fact pretty close to each other, particularly if you are obtaining that from the figure. Okay, so the next step is plugging the numbers into this correlation. So everything is checked at this time. ZH1 is checked, ZH2 is checked. T critical, I already used that, so I do have that value. This is checked, and RU, I already know the RU value. So if I put all these into this correlation, so let me just continue that here. That gives me H bar 2 minus H bar 1 actual or for real gas is equal to 23,081 minus 30,754 kilojoule per kilomole minus 8.314 kilojoule per kilomole Kelvin multiplied by the critical temperature, which is 647.1 Kelvin, multiplied by the difference in Z's, ZH's actually, 0.0223 minus 0.0288. So that will give me, if you do the number crunching, that will give you H bar 2 minus H bar 1 equal to negative 7637 kilojoule per kilomole. And finally, if you want to convert it into kilojoule per kilogram, all you need to do is to multiply that by the inverse of the molar mass. So that will give you H2 minus H1 equal to negative 7637 kilojoule per kilomole multiplied by 1 over 18.15 kilomole kilogram. Okay, and that will be negative 423 kilojoule per kilogram. Now, in case you're asking what is this number, this 18.015 kilogram per kilomole is the molar mass of water. So this is water molar mass, which comes from table A1. So this is the answer to part B. So the difference between them was negative 423 kilojoule per kilogram, or basically H2 was 423 kilojoule per kilogram less than H1. H1 was greater than H2. And in part A, we also had kind of the same result, pretty close, like these two numbers. I'm sorry, I'm showing here. So this is what we had in part A, and this is what we had in part B. So these two numbers are pretty close. In part C, the question is asking to make a comparison between the result that we have in part A and part B. So let me just write that on a new piece of paper. Okay. So part C is asking for a comparison between A and B. I would say, let me just write down, in part A, we use the superheated vapor table, and that gave me dH equal to negative 426 kilojoule per kilogram. This is what I used in part A. In part B, we use the enthalpy departure chart, and that gave us dH equal to negative 423 kilojoule per kilogram. So first of all, the two numbers are pretty close to each other. But the question is, between these two answers, which one is more accurate? So obviously they are different from each other, right? So one of them should be more accurate. The answer is the one that we obtained from superheated vapor table is the most accurate one, because those H values are listed for the correct pressure and correct temperature. There is no approximation done in those tables. So the answer to part A is more accurate. So here I mentioned answer obtained in part A is more accurate because it was obtained directly from the superheated vapor table. The thing is, in that table, we are looking at not only the pressure but also the temperature. So that means there is no approximation done in that particular table. Steam at that certain pressure and that certain temperature has this much of enthalpy. Now, this is different in tables like A17, A18, and A19. In those tables, they are ideal gas properties of different gases. And by saying ideal gas properties, we are only looking at the temperature. We are assuming that the gas is behaving ideally. But this is not the case in this particular problem. In this particular problem, we are directly in part A, we directly use the superheated vapor table. So because of that, the answers that we found in part A was accurate.